Assalamu alaikum again for today's lecture. Welcome to the first lecture of chapter 4. As you can see, the topic is solidification and crystalline imperfections in solids. Imperfections mean defects. Crystalline imperfections means that the defects that are there at the crystal level. Uh, as you know, today we have divided the lecture into two short portions. One short portion was finishing chapter 9 about engineering alloys and phase diagrams, and the second part of the lecture is about chapter 4. And as I said earlier, this is now basics of material science again, crystal structure and related imperfections or defects that are there. And by understanding this, we can understand why there are property problems or defects in materials at a higher level. I am using still the Smith and Hashimi chapter numbers. So in that book, sections 4.1 and 4.2 are solidification of metals and solidification of single crystals. So these two are not included. We will directly go to 4.3 is, as you see, solidification of metal solutions, right? So we will talk of this and then we will start. We have actually already talked of solid solutions with you earlier, right? When we make alloys, we melt them, we melt metals and so on, and we mix them together, they become mixture. And when they solidify, then this mixture is a solid solution, right? So alloys is another name, but any materials can be solid solutions and so on. Okay. Now I will talk only of the highlighted things on the slide. An alloy is a mixture of two or more metals, or a metal and a non-metal, right? Like aluminum, copper make an alloy, lead, tin make an alloy. These are metals. But iron and carbon is a non-metal, so that makes a steel, right? And as examples, you can see you have cartridge brass, you have Inconel, which is an aluminum alloy, and so on. So simplest alloy type is a solid solution. Solid solution. The elements are dispersed in a single phase structure, right? Simplest one. Just like, remember when we said binary isomorphous alloy. So there is, we have melted two metals, we have mixed them together, but when we solidify them, there is only one structure everywhere. There is only one structure everywhere. So that is a solid solution. We will talk just a little of it. Actually, we have talked about this earlier in alloys, but we will talk in more detail again. Now, solid solutions can be made in two ways, we will see. One of the methods is called substitution. So the alloy is called a substitutional solid solution. Substitutional. Now, what is the word substitute in normal English? I always ask you, substitute. Remember, when there is a football team, some players are there, some players are standing outside, and at some time there is a substitution. One active player goes out and another player from outside goes in. So we say a substitution has taken place. So this is exactly the meaning, that one of the things which is there is replaced with something else. So there is a substitute. So in a solid, if this substitution happens, then we have a substitutional solid. We will see that there is a chance of distortion in the solid. Distortion means that some shape change or something like that happens, some extra pressure or some force can happen inside. We will talk of solubility and of the Hume-Rothery rules of solubility. Hume-Rothery rules of solubility. And we have talked of these rules. There were two scientists, Hume and Rothery. And because they together found these four rules, that if there is a substitutional solid solution, then there are four rules. If these rules are followed, then solubility will be higher. And if these rules are not followed, then the solubility limit will be lower. In a very short while, I will show you the diagram, schematic diagram for substitutional solid solution. But let us see these rules. When we were talking of alloys, we told you this, that if there are two materials, for which we are making the solid solution, then the diameter of the atoms should not have a difference of more than 15%. This is the first rule. So if there is copper and if there is nickel, then the diameter of copper atom and the diameter of nickel atom, if the difference between the diameter is less than 15%, there are more chances that there will be a good solution. And if the difference is very small, only 3-4%, then it will be a very strong solution. But if the difference in diameters is more than 15%, then the solubility will be lower. This is the first rule. The second rule, the crystal structure of the two metals should be the same. If we have copper and if we have nickel, if one is BCC, the other should also be BCC. If there is lead and tin, if one is FCC, the other should also be FCC, right? In the case of iron and carbon, this rule does not apply because one of them is a non-metal. So then this rule is not to be used. But if there are two metals which are a solid solution in this alloy, then both should have the same crystal structure. If the crystal structures are different, then the solubility will be low. The third rule, you know electronegativity. Electronegativity, in chemistry you studied that because of electronegativity, things can make compounds and so on. So the difference in the electronegativity value should be small, not much difference. Not much difference. So if there are two metals, copper and nickel, then they should either have the same electronegativity or the difference in electronegativity should be very small. If this is not there, if the electronegativity difference is large, then they will make a compound rather than forming a solution. You see, we want to mix copper and nickel and they should mix very well together, but they should not become a copper-nickel compound. Otherwise, we don't have a solution, we have a new material, right? So the third rule is that the difference between the electronegativity of the two materials should be small. The fourth rule is continuation of the same. They should have the same valence value. If one is +1, the other one should also be +1. You see, so if their electronegativity is almost the same, their valence numbers will also be the same. So here also, they should not form a compound. If they have different valence numbers, then there is a big chance that they will form compounds. Now, compounds can be formed as electrovalent compounds and as covalent compounds. So if the valence number is different, then they form electrovalent compounds, +1 and -1. But if the valence numbers are close together, but the electronegativity difference is bigger, then they form covalent, right? So that is why the two rules are there, that they should have the same valence number and the difference in electronegativity should also be small. So if these two rules are satisfied, then it means that neither covalent nor electrovalent compounds will be formed, and therefore they will remain as mixture or solution. So these four rules are the rules for good solubility of metal to metal, and these were discovered by the two scientists Hume and Rothery rules, and they are therefore substitutional type of solids. Go to the next slide. Now this is a schematic representation. The light color, the pink color are one material, the dark color, the purple color are the other material, right? The dark color are the material. So this is it, that you see here originally there was this material, the original material, but this darker material came, removed the original from this place and took its place. So everywhere that you see a darker one, here originally there was the lighter material. That lighter material goes away and the darker comes in. So a substitution has taken place. So here, wherever it is, a substitution has taken place. The size, if you see, the size is almost the same. So the diametral size is the diameters of the two atoms. This is one type, that is the other type. You see, one of them, if the amount is larger, we call it the solvent. The amount is smaller, we call it a solute, if you remember. So the few materials, the few atoms, they are the solute atoms, and the large number of atoms, which are the more ones, are the solvent atoms. So the solute atoms are being dissolved into the solvent atoms. And the same rules are there, that the diameter of the solute and solvent atoms are almost equal to each other, and by some force and so on, because they start move, they have kinetic energy. So one of the solute, one of the dark atoms comes in and pushes out the light atom. So it is substituted. So this is a schematic diagram for a substitutional solid solution. Here, there are some examples of substitutional solid solutions. If you see copper zinc, copper lead, copper nickel are substitutional type. Why they are substitutional type? Because these things, difference in atomic radius is, you see here, 3.9. So this will be good solubility. Here it is 2.3, much less than 15%, good solubility. But copper and lead atomic radius difference is almost 37%, much bigger than 15%. So the chance of solubility will be very small. The electronegativity difference here is 0.1, which is a small. Here is 0, no difference. So this one and this one will have high solubility. There the electronegativity difference is 0.2, larger than this, so there will be less chance of good solubility. So here if you see solid solubility, copper zinc 3.9% atomic radius different, much less than 15%. Electronegativity difference of 0.1, which is a small. So 38% solubility, which is very good. Copper nickel, atomic radius difference 2.3%, which is very small. Electronegativity difference 0. So very high chance of solubility. So you see practically they found they are 100% soluble in each other. 100% soluble. But copper lead, very large atomic difference, low solubility, bigger electronegativity difference, low solubility. So only 0.17%, less than 1%. So there is almost no chance that these two will make a good alloy or a good solid solution. Right? So these are the things that this actually is practically done. But even if we know only these values, we can try to predict that the solubility of this material into this material will be very high or will not be. Let us proceed.